Okay, what I'm going to go through here for all of you is a sort of quick review of partial fraction decomposition. This is with the assumption that you've already had this in a pre-calculus course. So we're going to look at cases here. And partial fractions, if you guys recall, apply to rational functions. Where we want to write a rational function, a more complicated rational function, as really a sum and or difference of what we call simpler rational functions. We have simpler rational functions. So when we look at the first case of what we call distinct linear factors, that means different linear factors. Your focus is going to be, if you recall, on the denominator. So you have x squared minus 1. What we need to do is factor x squared minus 1. And that's going to be x plus 1 times x minus 1. So we can write this as one over x plus 1 times x minus 1, because that's what we get when we factor using algebra x squared minus 1. Now this is what they're referring to as being distinct, different linear factors. So recall, to be a linear factor, what does linear actually mean? Well, it's any factor of the form. We can write it as ax plus b. This is what they mean by having a linear factor. Anything that looks like this. The variable is x and the highest power is 1. So as you guys can see, we have two distinct linear factors. They're different. And that's what they're talking about. Now, this function, which is really going to be 1 over x plus 1 times x minus 1, partial fraction decomposition requires us to, in the case of distinct linear factors, write the rational function as a sum of two simpler rational functions. So here's our ax plus 1, here's the x minus 1, and then we need to find the constants a and b such that that sum is equivalent to the original function given. So this is, remember, how we approach the distinct linear factor cases. All right. So here we go. I'm going to bring out an algorithm for everybody to recall about how to add fractions with different denominators. Okay, so this is going to be something that we want to remember how to do. We cross multiply. So using this algorithm, we'll get a times d plus b times c over bd. So ladies and gentlemen, there you go. We're going to use this to cross multiply here for a numerator, and the denominator will have the product down here. So let's see what we end up getting here. Okay, so we end up with a times x minus 1 plus b times x plus 1 over the x plus 1 times x minus 1. So what you'll have, again, is 1 over x plus 1 times x minus 1. We're going to need some more paper here. Add a page. Okay. So we're also going to use, if you guys recall, a little piece of logic here. If I have two fractions, a over c equal to b over c, they have the same denominator here. Like what we're witnessing above. What that means is, then a equals what? B. So what you end up with is this equation that 1 will equal a times x minus 1 plus b times x plus 1. This is going to be what we use to determine the constants of a and b. So that's the idea behind partial fraction decomposition. We need to know the constants a and b here. So here's a, and I think we use purple for b. Okay, now there's various ways to find the constants a and b. There's not just one way, but there's various ways we can approach this. But the simplest situation is to focus on here the linear factors, x minus 1 and x plus 1. We're going to use a value of x that makes one of those linear factors 0. So in the first case, if I say, I'm going to let x be 1 now, okay? Because if x is 1, plugging in the value of x here will give you a 0. So that's what we want to try to do. And now the equation now here is 1 equals b times 2, because of the fact that 1 plus 1 is 2. Or we can just simply say that's 2b. Solving for b now by dividing 2 from both sides gives you b equals 1/2. So we have the first constant that we need. Okay, so we know b is the value 1/2. So maybe I'll just box it or something. Now, do this again. But this time, I'm going to say the value of x you want to use now will be to zero out this linear factor. So if x is -1, we're going to let x be -1. So wherever there's an x value, we let that be -1. What does that do? It zeroes out this linear term. We end up now with 1 equals -2a, because -1 minus 1 is -2. And so a is going to equal -1/2 now. So this is going to be the next, I should say, constant. So a is -1/2 and b is +1/2. So a is really the value -1/2. B is +1/2. So what we're seeing now by partial fraction decomposition, I'm going to bring this all the way down. is the original function of 1 over x plus 1 times x minus 1 can be described as, I'll put the positive term first, and let's leave this in blue because there will be some arithmetic, I guess, but the original function, x plus 1 times x minus 1, is negative 1/2 x plus 1 over x minus 1, which gives us 1 over 2 x minus 1 minus 1 over 2 x plus 1. So the original function can be described in a simpler way. Let's go back maybe to the beginning. We should just write it this way, I guess, as 1 over x squared minus 1 becomes 1 over 2 x minus 1 minus 1 over 2 x plus 1. All right. That's what they want us to do here. Here's another illustration where we have, again, a rational function. We want to write it as the sum or difference of simpler rational functions. But again, the denominator here is a quadratic. So when you factor this by using algebra again, we're going to get x minus 2 times x minus 5. Get 1 over x minus 2 times x minus 5. Again, we get two distinct linear factors. We want to write this as a sum or difference of what? Simpler linear factors. So for every linear factor, we have to write it as a constant over that linear denominator. Remember, these two are distinct linear. So every one of those linear factors is a sum, I should say, is a fraction, a simpler linear fraction, a over x minus 2 plus b over x minus 1. Now, x minus 5 in this case. So do your cross multiplication, and you'll end up with, again, a times x minus 5 plus b times x minus 2 over x minus 2 times x plus 5. So there's the factors. And don't forget that these fractions are equal. And so what that means is 1 is the same as what you see here because the denominators are the same. Now, what that means is the equation becomes 1 equals a x minus 5 plus b times x minus 2. So I'm going back and using a little bit of the logic I described earlier here for you guys. Let's see if we can see everything there. Using this statement. Okay. The numerator, and we'll change the colors down here just to kind of be consistent. Remember, this denominator is equivalent to this fraction here with the same denominator, which means 1 will be what we have there. That's what I'm referring to. Okay, now we're going to look at cases here for values of x. We're going to zero out this first linear factor by letting x be the value 5, because 5 minus 5 will give you 0. You're going to have to let this x be also 5, and you obtain 1 equal to 3b, because of the fact that 5 minus 2 will be 3. All right, now we can solve for b by dividing both sides by 3, and we're going to get, we never gave it a color, but that's okay, b equal to 1/3. All right, now we're going to repeat the process, but this time we're going to zero out the next term. And we're going to let x be 2 here. Let's bring this up. One will equal negative 3a, because 2 minus 5 is negative 3, and this becomes 0, which will mean a is negative 1/3. So a negative 1/3, b is positive 1/3. So I'm going to write it this way here. I'm going to write my positive term first. So I'm going to kind of switch. Well, we'll leave it that way. That's fine. X minus 2, x minus 5. I'll put negative 1/3 or positive 1/3 first, and then the negative 1/3. And so your final answer, that original function of x squared minus 7x plus 10 now becomes 1/3 x minus 2 over 1/3 x minus 5. And there you go. Okay. Nice quick little review. We're going to do the same here. And notice our denominator of x squared minus 5x plus 6 can be factored. As x minus 2 times x minus 3. So we notice again, we have distinct linear factors. Distinct linear factors. Linear meaning the x variable has a power of 1. So I'm going to write that here. So for every linear factor, we write it as a fraction. where you have a constant a over those linear factors. Cross multiply. So we have now a times x minus 3 plus b times x minus 2 over x minus 2 times x minus 3. So again, if we use the logic that we have a fraction equal to another fraction where they have the same denominator, the numerators are the same. So that means 2x minus 1 becomes a times x minus 3 plus b times x minus 2. Okay. Now, we're going to try to find the constants a and b by zeroing out these linear factors. So if you see that when we let x is 3, this portion becomes 0. X is 3. X is 3. So wherever there's an x, you replace it with a 3. Now in this example, on the left there is an x, so we're going to get a value there. And that's going to just equal b, because 3 minus 2 is 1. So we're going to get b equals 5, because 6 minus 1 over here is going to be the value of 5. Here we go. Okay. We're going to repeat the same process, but this time we're going to zero out the second linear factor over here. And you can do that by letting x be 2. So when you let x equal 2 now, this portion is 0. Now we'll get 2 times 2 minus 1 becomes negative a, because 2 minus 3 is negative 1. So you get 4 minus 1 is negative a, or really 3 is negative a. That means a will be negative 3. Okay. So we have our values. A is negative 3, B is positive 5, negative 3, positive 5. Here we go. So the original function of 2x minus 1 over x squared minus 5x plus 6 if again I write my positive number first, which is 5 over x minus 3 minus 3 over x minus 2. And since I'm writing those answers in black, I guess I'll just be consistent. And so, ladies and gentlemen, here you go. You're going to get your original rational function on the left here. written as a sum or difference of simpler rational functions. So this is partial fraction decomposition, distinct linear factors. Okay. Now, if you recall here, for partial fraction decomposition, you really need, if you hold on for a quick second, these powers can't be the same. Hello? Yeah. Okay. All right. All right. Bye. Okay. I apologize. Had a quick little call. We're going to have to do some division here, because the degree of the numerator has to be smaller than the degree of the denominator. So let's do some long division and remember how this works. Okay? We're going to take this first term here, the x squared. We're going to divide every term here by x squared in our first step of division. We'll end up getting 1 minus 1 over x plus 1 over x squared. Oops, I apologize. Sorry. Sorry, here we go. We're going to take that first x squared divided by x squared. Let me go over that procedure here for you. Okay, it's been a long time since I've done my procedure of long division, but anyway, x over x squared is 1. So here's the first step. So I put that 1 over the same type of term. It's a constant, right? So that's the first step, 1. The second step is to take that 1 and multiply it by the x squared plus x, which gives us x squared plus x. That goes below the terms that you see here. This is long division. The third step is to subtract. What we mean by that is you subtract the first polynomial with the second polynomial. That's the subtraction step. And what you notice is you get 0 here, and you bring down the 1, which is just going to be 1. Okay. So what does this mean here? We're writing this as a mixed number. You got a quotient, remainder, divisor. Your quotient is the 1, the remainder is 1, and you're dividing by that x squared plus x. So this becomes 1 over x squared plus x. Now, every mixed number is really, by definition, a whole number plus a fractional part. So you have 1 plus 1 over x squared plus x, and that's representing the original x squared minus x plus 1 over x squared plus x. All right. So now we can use on the right side partial fraction decomposition. We abbreviate that PFD, or I do that. Partial fraction decomposition on that first or I should say on the second term, the first fraction. So you're going to recall that we have to factor the denominator here. And this is why this is a distinct linear factor. Distinct linear. So I'm going to write this as a note here. So let's bring this down. Let's notate. That PFD applies to 1 over x plus 1. Which becomes a over x plus b over x plus 1. You have, again, distinct linear factors. All right, so now by our cross multiplication, really adding fractions that are not like, we end up with a x plus 1 plus bx over x plus 1. And that's really the fraction part of 1 over x times x plus 1 equals to what you see. Now, if you have two fractions again that are equivalent here, the numerators are the same. So we get 1 equals a x plus 1 plus bx, where again, we have a nice equation where we can zero out some of these terms by appropriate choices of x. Now, I want to make that first term, I'm going to start with that first term, make it 0. That can only happen if I let x be negative 1. So wherever there's an x, we let that be negative 1. And notice you get a zeroed out term here. And you get 1 equals negative b. Or we should say b equals negative 1. All right, b is negative 1. We're going to repeat that process again. And let x be 0. Because we're going to try to zero out the second linear term, and that is so kind of, this is just an x. So we're going to have to let x be 0 wherever we see the variable x. On the left, it's the number 1. We'll just have a here, and this is zeroed out. This is why we let x be 0. So what we end up getting is a going to be the value 1 now. A is 1, b is negative 1. So a is 1, b is negative 1. Okay. Let's bring this down. So what we're seeing here is really 1 over x times x plus 1 can be written as the sum or difference of two, we should say, simpler fractions here. Now, let's recall something here, because that's not the original function. That's only this part over here. Don't forget, we have the constant 1 to add. So, all together now, if we go back to the original, x squared minus x plus 1 over x squared plus x we get 1 over x minus 1 over x plus 1. Keep the constant 1 either before or after. It simply does not matter. But ladies and gentlemen, there you go. We simply wrote the original function as a sum or difference of simpler rational functions. And this is the case that we call distinct linear factors. We'll take a look at the other cases, but this is the end of this particular portion.